Okay, this is 7.4, factoring based on conjugate pairs. So I do want you to write everything down that you see here. The top half is here on this page. The bottom half is here on this page. And these are examples that we saw in Kurt's video. But I'm just going to use a portion of the examples he uses. All right, let's get started. So first of all, the vocab phrase conjugate pair. A conjugate pair is a difference between two perfect squares. So for example, I'm going to start with the most basic one. X squared. So x squared minus 1. Now, why is this a conjugate pair? Well, because x squared is a perfect square. It's found by multiplying x by itself. Okay? Now, 1 is a perfect square. And notice I'm not talking about the negative. I'm only talking about the 1 itself. So the 1 is a perfect square because it's found by 1 times itself. And the minus sign is very important here also because this is the difference. This is the part about it being a difference of two perfect squares. So the minus sign is the difference piece of that. Okay? Another example. We could go with 4x squared minus 4. 4x squared is a perfect square because it's found by taking 2x and multiplying it by 2x. And 4 is a perfect square because it's found by getting 2, multiplying it by 2. So it could be all sorts of things. It could be x squared minus 9. These are all examples of conjugate pairs. I'm going to give one more. Let's throw the variable at the end, like 25 minus y squared. Again, two perfect squares and the difference of them. So those are perfect squares. Those are the difference of two perfect squares, and they're called conjugate pairs. Okay? All right. In exercise 1, Kurt did these, but I want to first do letter A using either double distributing or FOIL. It doesn't matter what you want to call it. I'm just going to show my arrows. So x times x, and then x times negative 5. Oops. Oh, brother. And then x times, nope, made a mistake. Positive 5 times x and positive 5 times negative 5. Now, take a look at this. The reason that all three of these, A, B, and E in exercise 1, the reason all three of these are going to turn into a conjugate pair is because the two like terms will equal 0. So some people say they cancel out. They eliminate each other. Okay? What you're left with is x squared minus 25. Okay? So we'll do it a little faster because we notice something. We start to notice that the last term of both binomials, the 5s, got squared to give us 25. And then we notice that the first term of each binomial got squared to give us x squared. That's really all this is saying down here. And we'll get to that in a minute. But let's use that pattern and try it on B and E. So let's just square x. And let's square 2. But notice something else. Remember what we said in the beginning. It's the difference of the two perfect squares. Okay? Because notice what's here. It's not just any 25. It's a negative 25. Because this is a negative 2 times a positive 2 over here. Negative 2 times a positive 2. That's where that negative comes from. Let's try it on letter E. Square the first term, 2x times 2x. So in other words, multiply the first terms, and we get 4 x squared, and then multiply the last two terms. We get negative 9. Now, I can trust that this will work because if I were to do it the long way, I would get 4x squared, negative 6x, positive 6x, negative 9. And what's going to happen? Those inner terms, those like terms, they equal 0. And look what we're left with. 4x squared minus 9. Same thing, right? Same thing. Okay. Now, there's something else that's important to point out. The only reason this works is because each of these binomials are practically identical except for their sign. Okay, take a look at A, B, and E. A, x plus 5 times x minus 5. Look at B, x minus 2 times x plus 2. Look at E, 2x plus 3, 2x minus 3. Those are the characteristics that make these factors that produce or result in conjugate pairs. Okay, that's why all of these make conjugate pairs. All right, let's check it out in example exercise 2. So take a minute now, again, if you haven't done it yet, write down this box, okay, with the information inside. Notice that A plus B is multiplying A minus B, okay, and we get A squared minus B squared. That's the pattern that we noticed in exercise 1. So now we're going to do it real quick in exercise 2, okay? X squared, so A in this case, so the A meaning the first term in each binomial, in this case, is x. So let's square it. We get x squared. Okay, what's our B in letter A? I know I'm throwing a lot of letters out there, but what's our B? Our B in letter A, so in this problem, our B is a 6 and a 6. More specifically, it's a positive 6 and a negative 6. So we're going to multiply those. What do we get? Negative 36. Okay? All right, let's give it a try. So in letter B, let's be a little more careful. Let's double check. Do we have the same first term in both? Yes. Do we have the same last term in both? Yes, but they're opposites. That's what we want. We want the same number, opposite signs. Okay, are they being multiplied? Yes. Okay, in other words, these two binomials are being multiplied. This means we can use the rule for multiplying to get a conjugate pair, multiplying conjugate pairs, okay? All right, let's see what we get. 5x times 5x, 25x squared. Positive 2 times negative 2, negative 4. Okay, letter C. Do we have the same first terms? Yes. Do we have the same last terms? Yes, but they're opposites. That's good. That's what we want. Let's try it out. 2x times 2x, 4x squared. Positive 7y times negative 7y, negative 49y squared. Good to go. Okay, pause the video if you need to. Write down what you need to. We're going to move on to the bottom part of the notes. Okay, here we go. So I just kept this part up here in our notes so we could reference it whenever we needed to. Okay, we're checking to make sure that we have conjugate pairs so that we can get the difference of two perfect squares. Okay? All right. Here we go. Exercise 2. That's the one we just did, so that was an accident. We don't need to do that again. Let's jump down to exercise 3. As we saw in Kurt's video, Amelia and Isabel tried to factor x squared minus 9. Let's underline that. Each of their answers are below. distribute their answers. So distribute to prove that these expressions are not the same. So we want to prove that they're not equal. All right, let's give it a try. I'm going to do this the long way, though. I'm not going to skip any steps. So first of all, notice these are not, Amelia's work are not conjugate pairs. So we know something that Amelia hasn't caught on to yet. These are not conjugate pairs, therefore they will not equal the difference of two perfect squares, okay? Let's show that work. X squared, x times x, and then x times negative 9. And then on the second term, so positive 1 times x, and positive 1 times negative 9. Okay. It's not promising, not looking promising. This cannot equal this difference of two perfect squares. So let's keep going. X squared, what's negative 9x and positive 1 makes negative 8x. And then don't forget about the negative 9. This is as far as this goes. Amelia did not factor it correctly. Let's see what Isabel did. Isabel's looking much better because look at what she's got. She's got x minus 3 and she's got x plus 3. The first thing I notice is that her x's are the same. Her last terms, negative 3 and positive 3, are opposites. And that's exactly what we need in order to create the difference of two perfect squares. So let's check this out. We'll do it in two different colors. X squared, so that's this first part. It's a little crowded. X times x, we get x squared. X times positive 3, we get positive 3x. X times, oops, that's a mistake. Negative 3 times x, we get negative 3x. Negative 3 times positive 3, we get negative 9. This is promising because look at those like terms. They're going to equal 0. So we're left with x squared minus 9. Isabel was doing it correctly. So they are not the same. They are not the same. When in doubt, multiply it all the way out. Okay, you can move on to your next part of OMA number 30.